Hi, this is Tariq Rashid. Today I'm talking about a new algorithm, which is called LEO. It stands for Lagrange Elementary Optimization. The algorithm is actually designed by Asu Al-Adin and myself. The more details about the algorithm can be found in the below links. I'll go through the algorithm step by step and explain details of every step in the following slides. So Lagrange Elementary Optimization, it's a new algorithm, stands out as a novel evolutionary approach in the world of global optimization. LEO is a meteoristic algorithm. It takes its inspiration from genetic algorithm, which is a very popular algorithm. LEO is a self-adaptive algorithm, takes its inspiration from high precision of vaccination that leverage the albumin quotient in human blood. LEO dynamically or robustly adjusts its optimization process, reflecting the adaptability of vaccination to individual immune responses. The creation of intelligent agents relies on gene crossing and utilizes the fitness function value. Mathematical adjustment, a new optimal solution is achieved through utilization of a novel algorithm operator based on Lagrange dual function, LDF, and LPX based on LDF. LPX is developed by our group. Details of LDF can be found in our previous videos in the links that's shown in the first slide. So LDF demonstrates the essential Lagrange elementary duality gap property, which plays a pivotal role in achieving a deterministic solution. Improving Lagrange dual functionality is to facilitate the crossing of selection genes within the group of agents, resulting in the provision of new genes. Now, this is the LEO adjustment, LEO model adjustment. These mathematical details, I explained them in my previous video, which you can find the link in the first slide in this presentation. So feel free to go back to it, and the video is very explained in detail everything. So therefore I skip this slide. Now, if we take a population of 5,000 individuals, we try to initialize our sample. The actually algorithm tries to start by initializing albumin serum and the population at random in the search space or population. And we try to choose the most effective immune system, IgG, among multiple positive systems. Now, if the termination condition is not met, it will be used as a parameter to select percentage of individuals at random from N. So this is X over X Ti plus 1. That's the equation, which is the, we're trying to find the, fitness evaluation, which is albumin quotient equals albumin CSF over albumin serum. Now, LEO parameters are these: the main population, the number of parents, and mu. It's a parameter to divide the sample into two groups, and then the iteration, Then we have half group, first group of the half group, and second group of the half group. Okay, so and K is the calculated number of newly created parents by counter. Now the algorithm works by having mu parameter to divide the percentage and evaluate the fitness individuals X. Then according to fitness function, we sort out in a decremental way, and then we go through individuals in the first group, and if it is higher than or equal the main fitness of the half group, of the first group, then it will be selected. Otherwise, they won't be selected, or we select individuals from the second group. Okay. Now, this slide talks about the LPDF, which is the theory, conic duality theory, which we created our LPX from this theory, Lagrange problem crossover LPX. And we have a paper in the link in the first slide, and these equations are all explained in detail. So I'm also skipping this one because we have 2 more videos to talk about all the literature review about the crossover operators. And also we have a video about LPX and Lagrange Elementary Optimization. Now, after crossover, we use this equation to make a mutation. So selection, crossover, mutation, and evaluation, and then selection, crossover, mutation, and the process goes like that. So that's the mutation, and that's the random size of the sample population, and this is the sigma, which can be a parameter. Then the mutation will be the mutant solution. It will be like that. Now, this is the algorithm: start, initialization, and then identify Leo parameters, and then make a randomly divide the population into 2 groups, select the highest fitness, and then traverse through the first group individuals, compare them to the highest fitness. If it is higher or greater, then will be selected. If not, then we will select from the second group. Leo were compared and evaluated against FDO, LPB, PSO, genetic algorithm, and Dragonfly, and measured by 19 classical benchmark tests. Leo also tested against CEC 2019 test functions, and the algorithms that Leo competitively outperformed were Dragonfly, WA, SSA, Fitness Dependent Optimizer, Learner Performance Base, and Fox algorithm. Now, some p-values, statistical tests were conducted to show how good our results are. Now, also, on top of this, we have used 2 real-world applications or problems designed by the authors of Leo, the pathological IgG, fraction in the nerve system, and integrated cyber physical attack for manufacturing system. Now, we will have a case study. I'll go through them. If we have a population of 5,000 individuals, we select 20 randomly, and this is our fitness function. The upper bound and lower bound for X1 and X2 is 1 till 100, X1 to 1 to 100. Now, these are the populations were selected from the 5,000 Okay, and these are the numbers were selected. Fitness function was found, and we found the sum of the fitness average and max and min. Now we go through the x1 over x2, which is albumin CSF over albumin serum, and we find fitness value. We find fitness value. We find fitness value. So these are the fitness value. These are the fitness value. So and then we will have, we will find that x1 over x2 will give us 31. 31 is the highest among all. So we're going to compare all individuals, all fitness values against 8,658. If they are bigger than 8,658 or equal, they will be selected in the first group. If not, then they will be kicked out, and instead we will select those individuals from the second group. Okay. Now here in the green, those selected, they are higher than 8,658. You can see those all higher than this one. These two are lower. This one, these ones are kicked out. Instead, we will take these two greens from the second group and lift them up to the first group, and then we will have 10 individuals. So the other 10 were kicked out because of their fitness are less than the highest fitness. Now we do crossover using equation 2 and 3 in the previous slides, okay? And we try to take C1 and C2. If I just go through the previous equations that we say 2 and 3, this one, 2 and 3. So we use these two equations to find C1 and C2. And then after that, we will try to find offspring or so here we will try to find with this formula, because we have C2 and over X1, we'll find O1, and likewise we will find O2. These are the values for them. Now we do the mutation using equation 4 in the slide, sigma, which is taken minus 0.3, random size 20. Here we will find M1 and M2. Now the all individuals, we have them here, 20 individuals, they will be selected for the next iterations. And these were found from the crossover, and this one, the 10 that we selected. So this 10 from we selected, and this from the crossover. Now we will find in this slide some fitness, average, max, and min. They will be used for the next iteration. Now, next iteration, again, we will do the same process. And we found that x1 over x2 will get 6.3. So this is the highest. All these individuals will be compared against this. And if they are higher or equal, they will be selected. If not, they will be kicked out. Instead, we will select individuals from second group. Now we found 6.3, and this is the fitness value, which is the highest. Okay. Now these are selected, and these are selected based on the criteria that we had, and then we do the crossover. C1, C2 will found, and then we do mutation and O1 and O2, and then we will have the whole individuals found. Now, then we'll do the same, and we go through them, and we will. In this slide, in this presentation, we will show 3 iteration steps, and you can see that the results are improved. Now, if you have any questions or issues, please email us. Our emails are on the paper and in the links. You can find them, and I wish you all the best. So these are the links. Thank you very much. All the best.